Okay, we're looking at circles, circles, circles. This is the first page of the HP11N underscore Trinity underscore Corona notes for rotation. What we're looking at here is circular motion and circular kinematics. If you've seen a previous video where we went from linear to angular conversions, this will be familiar. But a quick little overview of what is a radian. In your math courses, they may have shown you this, but if you have a circle of some radius r, this edge out here, if it has radius r, you can actually go around your circle. That last one's bad. You can go around 1, 2, 3, 4, 5, 6, and that actually should be about here. 6, and then a little bit of extra. And it turns out if you go around that circle 6 and a little bit of extra, you've actually gone around the circle 2 pi radians of measure. Okay? That 2 pi radian measure is equal to 360 degrees. It is just a measure of how much angle you've gone around if you're going around a circle in terms of the radius. So that's what we're looking at there. Now, because of this moving along a circular path there, and if we look at our angular to linear conversions, we can say that an angle can be thought of as a linear distance divided by the radius, and that's because if you look at your old best friend, we can see that the linear distance s or x, depending on how you like to write it, can be thought of as theta times r, okay? And that's all on our best friend sheet. Now, what we're going to look at here is we're going to look at some rotational kinematics, which is just how do objects speed up and slow down, and how do they move whenever they're undergoing motion, whether they have a speed and they have an acceleration. So how does that kind of work for us? So what we're going to do here is we're going to first note that if an object has a constant angular velocity, then we're only using equation 1r. Equation 1r, if we go and look at the sheet that we filled out on previous videos, equation 1r is stating that an angular displacement is equal to an angular velocity multiplied by a time. Or a few other ways to write this could be that a angular velocity is equal to an angular displacement divided by time. Notice that in both of these equations here, there is no acceleration. There's no angular acceleration here, okay? And if we have a constant angular velocity, then we don't have an acceleration. We are at a constant rate. So what some of the skills that we need to be able to do in looking at these is we need to be able to convert between revolutions and radians. So if you had 2 revolutions, how many radians have you gone? And then how can you relate your linear distance to an angular displacement and vice versa? So the example we're going to look at here deals with a car, and this car has a tire on it with a radius of 0.38, so I'll talk that to the side, r equals 0.38 meters, and it rotates 4.5 times. So that means it has 4.5 revolutions, and it has a time of 0.75 seconds, or 3/4 seconds. If we want to figure out what is the tire's angular displacement in radians, then, well, we are actually just doing a unit conversion there. An angular displacement, remember, is a theta. And what we have here is revolutions. 1 revolution, remember, is 2 pi radians. So with that unit conversion, we can quickly go from 4.5 revolutions to some amount of radians. If we write this with a train track, fence post, unit analysis method, whatever you want to do, we know 4.5 revolutions, there are 2 pi radians in 1 rev. And when we look at this, we see that our revolutions, they divide out. They've canceled, as some say. And I'm going to do something that's a little strange at first to look at, but we'll quickly get used to it. I am going to multiply the 4.5 and the 2 to get a 9. But I'm going to leave the pi there. I'm going to leave things in terms of pi. And we do that because it's very helpful to start thinking about radian measures as being values of pi as we go around that unit circle, so to speak. Okay, so 9 pi radians is our answer there. If we wanted to find an angular velocity, well, we could go back to that equation, number 1r. We could say, hey, look, I'm looking for an angular velocity there. All I need is an angular displacement in radians and divide it by a time. So omega equals theta over t. That's going to equal 9 pi radians divided by, well, 0.75 seconds, or 3/4 seconds. 9 divided by 3/4 is going to be 12, and I'm going to leave this in terms of pi. Looks a little weird, makes life easy because I don't want to multiply by that. My units are in radians per seconds. This is a velocity, but it cannot be meters per second because we're rotating. I care about how much angle I'm covering in amount of time. And a unit of the angle is radian, and in an amount of time is seconds. So there it is, 12 radians per second. That's our second answer. If it's moving at this speed, and by this speed what we're talking about is the omega above, what's the angular displacement, theta, that it would make in 1.2 seconds? So now we're just letting it spin a little bit longer. And in doing this, we're going to have that theta is just equal to an omega times t. We know the omega here. That omega is the 12 pi radians per second. And we're just multiplying that by a time of 1.2 seconds. We easily see that our denominator and numerator of seconds go away. And I'm still going to leave this answer in pi. It's going to be 12 times 1.2, which I don't know what that is, so I'll just pull out a calculator. 12 times 1.2. That's 14.4. So we've got 14.4. Don't forget your pi. Don't forget your pi. And that's going to be radians, because that's the only unit I have left. Okay? If we'd like to figure out then, how far does the car travel in this amount of time? Anytime we see the words how far, we need to be thinking that this is a linear quantity. Like physically, how far away is it? So what we have to do is we have to take our theta and we have to somehow get it into an S value. Well, this is actually easily doable. We know that S, a linear value, is just equal to an angular displacement multiplied by a radius. This is just the idea of if your wheel has rotated multiple times, how far have you traveled? How, if you painted that edge of the wheel, how much paint have you laid down on the ground? If you had a very small wheel, if this R value was very small, then whoop, 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 you haven't traveled very far. But if you got a big monster truck wheel or something, if that thing rolls once, you could travel, 10, 20 feet. So this is how we convert between angular and linear quantities. And in our case here, when we do this, we know what our angle here is. It's 14 pi, or 14.4 pi radians. And then we need to multiply by the radius of the wheel. And that wheel's radius, if we go back to the top, was 0.38 meters. So we'll come back down here. We'll multiply that by 0.38 meters. And we'll get a value here. The value we get here is 14.4 times 0.38. And that would be 5.47 pi somethings. You've never opened up a Google map and it said, the grocery store is 2.38 pi miles away. Because these are linear quantities, we actually want to multiply by the pi. We just want a final number as our answer. So when I multiply by the pi here, I actually get 17.19. Now the other thing that's strange is The units you have left are radians and meters. You have both of them. But radians are not a physical unit. Radians don't actually apply to the real world for a physical quantity. Radians just kind of tell you, well, how much have you rotated through a circle? They don't tell you if it was a big circle. They don't tell you if it was a small circle. It's just you've rotated. And because of this, our units here are not radian meters or meters radians. They're just meters. Just like if I was saying, hey, go to the end of the street 2 miles away. It's just miles. They're not radian miles or anything. So that's an important thing to keep of. Even though you have 2 units here, we really don't care about this unit. It's not a real quantity, so to speak. It just gives us an idea of how far we've actually moved in a radial world. So that right there is some quick little kinematics. Remember, these are constant velocities here when we're doing this, so we're only use equation 1r. We don't have an angular acceleration, but we do need to be able to equate linear and angular quantities by these angles times a radius value. Okay? Check out the next video regarding some more complicated kinematic motion for rotational quantities if we're accelerating or decelerating, like a ceiling fan. So take it easy. See you on the next one.